Lesson 2.5, Non-Equilibrium and Fundamental Forces. There are four basic forces. All other forces are made up of these four forces. We have gravitational force, which is due to gravity. We have electromagnetic, which deals with static electricity and magnetism. We have weak nuclear force, which has to deal with radioactivity. And we have the strong nuclear force, which keeps the nucleus of the atom together. And actually, all of those have been kind of combined in what's known as the unified theory, the grand unified theory. However, gravitational force has not been combined to those yet. But we still like to think of these as four separate forces. All forces occur because particles with that force property play catch with a different particle. For example, electromagnetic, so charged particles throw a photon back and forth, and that either attracts or repels the two particles. Scientists are trying to combine all the forces together in the grand unified theory, and we've combined electromagnetic and weak nuclear. And last I heard, I think they've kind of gotten strong in there too, but the gravitational force is still causing issues. Of the forces, gravity is the weakest. We feel it because the electromagnetic cancels out over large areas, and gravity doesn't. Nuclear forces are really strong, but only over short distances, very short distances, as in the size of the nucleus of an atom or smaller. Let's say a 1,380 kilogram car is moving due east with an initial speed of 27 meters per second. After 8 seconds, the car has slowed down to 17 meters per second. Find the magnitude and direction of the net force that produces the deceleration. All right, so here's my car. All right, so we've got some normal force on this car. It has some weight on the car. And then what's slowing the car down? Usually we call that some sort of friction, drag, whatever. So that would be, I'm just going to call it F for friction. Okay. So I could work in my forces. We'll start in the Y. So in the Y I have normal force up and the weight down, and I have no acceleration in the Y. The car is not flying up off the road or digging a hole down into the road. So my normal force is going to equal 13,524 newtons. If I go in the x direction, I have my net force equals ma. So that is just the negative F, which equals ma. And there is acceleration. It says there is acceleration. But do I know the force that's slowing me down? No, it's what I'm supposed to look for. And I don't know my acceleration. So I'm going to have to use some kinematics to find my acceleration. What do we know? We know our initial speed is 27, and we know our final speed is 17. We know our time is 8 seconds. I'm looking for my acceleration. So I could say v equals at plus v0. Subtract the 27. and then divide by the 8 seconds, and I get negative 1.25 meters per second squared. So I can fill that in for my acceleration, and I end up with negative F is negative 1725 newtons, or our force that's slowing us down is 1,700 and about 30 newtons if I use 3 significant figures. And which way is it going? It is going west. A supertanker of mass that is being towed by 2 tugboats as in the picture. The tensions of the towing cables apply forces T1 and T2 at equal angles of 30 degrees with respect to the tanker's axis. In addition, the engines produce a forward driving force D, and the water applies an opposing force R. We have an acceleration forwards. We're supposed to find the magnitudes of the tensions. Well, since the tensions are at an angle, we're going to have components. So it'd be T1 sine the angle. So it'd be T2 sine of the angle. And in the middle, it'd be cosine. If I start with the y direction, the vertical, I'd have T1 sine of 30, because that's the force going up, and then T2 sine of 30 down. Now, I don't have weight normal force here because I'm doing, this tanker's flat, the weight and the normal force are going to cancel out. This is the net force equals ma. The acceleration is in the x direction, not the y direction. Add the T2 sine 30 to the other side. We get T1 equals T2. In the x direction, if I go net force equals ma, got R going backwards, D going forwards. I have T1 cosine of 30 going forwards and T2 cosine of 30 going forwards. And that should equal mass times acceleration. The R is 40 times 10 to the 3 newtons. The D is 75 times 10 to the 3 newtons. T1 I'm looking for. Cosine of 30 is square root of 3 over 2. T2 is the same as T1, so that will give me another T1 square root of 3 over 2. Our mass is 1.5 times 10 to the 8. And the acceleration is 2 times 10 to the negative 3 meters per second squared. So 35 times 10 to the 3rd newtons. Square root of 3 over 2 plus square root of 3 over 2 would just be the square root of 3. T1s equals 300,000 newtons for the MA. Subtract the 35 times 10 to the 3rd, and we get 265,000 newtons. And then divide by the square root of 3, and I get T1 to be 153,000 newtons. And T1 and T2 are the same, so T2 would also be 153,000 newtons. A flatbed truck is carrying a crate up a 10-degree hill, as in the picture. The coefficient of static friction between the truck bed and the crate is 0.35. Find the maximum acceleration the truck can attain before the crate begins to slip backward relative to the truck. All right, first of all, let's remember, since we're going up a slope, it's easiest if we rotate our axes. Call the x parallel and the y perpendicular. Which also means that we need to find the components of the weight. Since that's 10 degrees, this one would be our weight, and it's opposite the angle. So it would be sine 10. This other one would be the weight cosine 10 because it's adjacent to the angle. Because I'm using friction, I'm going to need to know the normal force. So I'm going to start in the y's, which is the perpendicular component. Net force equals ma. I have normal force up, and then the perpendicular component of the weight down. But we're not accelerating in the y. We're accelerating parallel to the slope. We're not flying up off the slope or digging a hole through the slope. So my normal force is going to be mg cosine 10. Now if I look at the parallel, and net force is ma. So in the x direction, I've got the friction going uphill, which I'll call positive, and the weight, the parallel component of the weight, going downhill. Friction is the coefficient times the normal force. Our coefficient is 0.350. My normal force is mg cosine 10. I don't know the mass. However, I see I have a mass everywhere, so I could divide both sides by the mass. And then the mass is going to cancel out. So let's fill in the 9.8 for G, because we assume our truck is on Earth. And run that through the calculator, and we get 1.68 meters per second squared. So that is the acceleration the truck can have going up the hill without losing its load. A window washer on a scaffold is hoisting the scaffold up the side of a building by pulling downward on the rope as in the picture. The magnitude of the pulling force is 540 newtons. The combined mass of the worker and the scaffold is 155 kilograms. Find the upward acceleration of the unit. All right, so first of all, it says he's pulling down on the rope, so why is the tension pointing up? Because we want the forces acting on our object, not created by our object. So if he pulls down, the rope pulls back up on him. That's our Newton's third law, reaction force. The same rope is connected to both sides of the pulley, hence I have two more tensions. So if I go net force equals mass times acceleration, I have three tensions upward and the weight downward. Our tension, it says he pulls with 540 newtons, so that's our tension. Our mass is 155 kilograms. G, of course, is 9.8. Mass is 155 kilograms. Okay. And So we get 101 newtons. Divide by the 155, and I get 0.65 meters per second squared for the acceleration of the guy and his scaffold.